The next presentation will be about the chapters 10 and 11, MEP systems and operation and maintenance by Arianna Minoret. So I will ask Arianna to share her screen.
So chapter 10. Chapter 10 is on mechanical, electrical, and plumbing system. I will bring some examples, especially from the Norwegian studies, to exemplify the described concept. This is also based on the idea that the authors involved in writing the design guidelines of the Submerged Floating Tube Bridges should bring their experience with the idea to share the knowledge with the global scientific community. Generally, we can say that any normally applicable requirement for immersed or bored road and rail tunnel system shall be considered also valid for a submerged floating tube bridge. The focus on this chapter on mechanical and electrical system of SFTBs is on systems or characteristics or requirements that are specific for this type of structure. Regarding traffic management and closed circuit television, also known as surveillance cameras, these are part of the MEP system. The SFTBs require a traffic management system and a surveillance camera as any other tunnel. For example, to avoid too many vehicles in the SFTB because accumulation of traffic will increase the congestion in case of an evacuation. Surveillance cameras must be located also along the safety path in the main structure and in the connections, so in areas that are not in use in the situation of normal operation. In the picture, you see a scheme for the escape tunnels in the transversal connection for the twin tube bridge. And in addition, the traffic signs along the wall crossing will help the drivers, for example, to keep velocity under control and to keep safety distances. As for tunnels, thermographic control of heavy vehicles at the entrance of the approach tunnels for the SFTB can prevent the entry of overheated vehicles into the tunnel. So this is a picture taken from the Mont Blanc tunnel where two thermographic gates are located to check any overheating of engine parts of lorries and buses. The experience shows also that several cases of explosions were generated by fires that were already present on commercial vehicles. So this is, of course, a very important topic for the SFTB, where we must take into consideration the confinement effect for a blasting load as any other type of tunnel, but also the requirement of integrity of the structure exposed to this type of loads. This is also why a consistent effort has been done in the tests and simulations for these specific load. In the picture, different cross sections are shown with the position of the charge, and these simulations have been published together with other fire and explosion tests in scientific journals, so it is available for everyone. Air quality and small ventilation. Ventilation systems are used to avoid high concentrations of toxic gas generated by fossil fuel car engines. The required fresh air volumes depends on the traffic density and the tunnel length. Mechanical longitudinal ventilation is often used, and as for immersed tunnels, the possibility to use of intermediate ventilation towers is limited, and ventilation systems that do not require intermediate ventilation shafts and towers are therefore preferred. But in the design phase, we have to consider that these might require additional longitudinal air channels. So for sure, the growing market of electric cars could help to reduce the requirements for the ordinary ventilation, but we have to consider that mechanical ventilation is also used to create safe zones in the event of fire. Conventional longitudinal ventilation in the event of fire operates at low speed, and the direction shall be in the traffic direction. coordinated with the evacuation plan, but also additional horizontal exhaust shaft could help for the smoke ventilation. And regarding fires, even if passive fire protection is provided, automated fire extinguishing needs to be installed as well. Fire extinguishing water must not accumulate in the tube. It shall be drained and pumped away simultaneously with the fire water supply. In the picture, the cross-section for a submerged floating tube bridge and a plan view of the transversal connection between the two tubes is shown, with the available areas where the system can be located. And speaking about drainage and pump system, the SFTB is similar to a subsea tunnel. Usually the tube is submerged and the access in both ends are above ground, so pumping will be necessary to ensure drainage of the SFTB, and the longitudinal slope of the structure must be taken into account for the design of the system. For a mainly horizontal tube, the water will not move for over large distances, and these must be taken into account. The system shall be over-designed and shall be inspectable and easy to clean, to remove sediments and clogging. The materials shall be saline water resistant. Fire extinguishing water reserve tanks shall be included in the design, and the relocation of the associated weight shall be included in the design scenarios. If an automated bilge pumping system is part of an inherent safe design, it shall be equipped with a separate independent power supply and an offline control system. It shall be subjected to periodic inspections, test runs, and a certification program. Pump engines and control systems shall be located where the risk of flooding is the lowest. So this picture shows a plan scheme done for the Bjornafjord, where reservoir were located at both tunnel ends with a remote monitoring of the level. In the design stage, also the need to separate sand traps, eventual need to separate sand traps, oil separators, and so on must be evaluated. And the connection elements between the tubes located, for example, every 150 meters can be shaped, taking into account the needs of drainage and water collection. So in this drawing, you see a model done for the Bjornafjord crossing in Norway with this cross section connecting the two tubes. Of course, several considerations must be done. For example, to reduce the required pumping energy, it is recommended that the drainage water is pumped in series from the middle of the SFTB and to each end. It is foreseen that each pumping station has 2 pumps with the rated capacity, and there will be pump lines in each tube tunnel, and this for redundancy. The pumps can be submerged pumps placed in the reservoir or dry pumps placed on the outside. We can say that external pumps will be easier to maintain if a suitable location is available. The pumps will be monitored and controlled remotely, as control and monitoring of valves will be from a remote control rooms. For measuring of level indication, ballast tank requires particular attention. The system must be designed not only for the operation of the structure, but also for the temporary phases. The design of the ballast is done from the early phase in the design procedure and must take into consideration several aspects that are connected with the design choices for the structure, like, for example, the amount of solid water ballast, or on having a passive or active ballast system that implies different setups and system installed. But the operational conditions of the structure are not the only ones that we have to take into account. For example, we have also to provide the necessary system taking into account all the installation phases. As an example, in the picture, the floating sequences for the submerged test and the installation of a pontoon, SFTB, are shown. So several choices must be done, for example, regarding the possibility of doing the ballast operations remotely, controlled or just manually, regarding the possibility to have permanent connections between ballast tanks and pumps, manual valves or remote control, and so on. Every choice implies different systems to be provided, and it is suggested, as we will see in the next presentation, to do choices that limit the amount of inspection and maintenance of ballast equipment, and also minimize the risk of maloperation of the ballast system. For safety purposes, it is suggested to not to have direct connection to the sea after the installation. At last, I can say that usually compartments used for permanent and temporary ballast tanks are not intended to be filled 100%, and control sensors have to be installed. So also for the ballast, the position and the redundancy of the system must be taken into account for safety purposes and concept robustness. In the picture, an example of a temporary ballast phase to empty the intersection is shown in the section of the bridge. For the studies done in Norway, for example, the possibility of using portable pumps connected to the system adjusted during the use has been evaluated for several operations as a safer solution, also in terms of reducing the possibilities of maloperations in the long term. And as it is necessary to check the freeboard for safety purposes, it is also necessary to include permanent force and displacement measurement systems. This system is also a cost that must be taken into consideration during the feasibility study of the crossing. So this means that in the design optimization procedure, it is more convenient to enlarge the single tether than to design a bridge with a higher number of tethers. Electric power supply for lighting and for a safety system and the safety system themselves shall be made redundant and invulnerable for local problems like collisions, traffic accidents, or leakages, or global power cutoff. The electrical system must be designed for the specific requirements of the SFTB. So for example, as we can see in the picture shown, a system of lighting to interrupt the perception of the entire tunnel length could be interesting for longer pedestrian crossings. Or as another example, a night lighting system could be evaluated for a pontoon SFTB for safety purposes. Lighting the pontoons could be an additional way to locate their position for the passing vessels, but ship collisions are not the only possible collisions that must be considered. Submarine collisions could also be, for example, an issue. If a sonar reflector system is installed on the structure for the detection by floating or submerged vessels, which could collide with the structure, a passive system is recommended instead of an active one. And this is due to the proven negative effect that the active system has on marine mammals. So this was an overview of the content of chapter 10 on the MEP system for Submerged Floating Tube Bridge. Now we go on with chapter 11. That is the chapter on operation and maintenance. As we have seen in many of the previous chapters, in more or less all the choices done during the design of the structure, we have to already take into account the operation and maintenance procedures. And this must be done to design a structure with the principle of minimum maintenance. This is not only a matter of cost connected to the maintenance procedure. A minimum maintenance means a safer structure because it obliges the designers to work on the robustness of the concept and obliged to make choices that will guarantee the durability. And this implies a lower use of new materials during the life of the structure, with a consequent reduction not only for the maintenance costs, but also for new emissions in the environment. Of course, this requires an effort in the design stage where we will have to think about the life of the structure and make choices that will allow to inspect every part of the structure, for example, directly or with measurement system, foresee the challenges that the structure will have to face during its life and protect consequently the structure or prevent dangerous situation, or to choose a strategy for the maintenance of the structure, evaluating performances and cost. So we have to focus on inspectability, protection, prevention, and life analysis with related strategies as shown in the right part of the picture, where performances in time are shown. Then this depends on the strategy chosen. So for the maintenance of the different parts of the structure, it must be considered that the design life can be different for each system, and consequently, different maintenance strategies could be necessary. So here in the right part of the picture, well, it's a bit small, but maybe you can see it. You see several elements in the cross section that are relevant for the operation and maintenance. And in the left part of the picture, you have an overview on the design life for all the different elements. And as you can see, these can be really different for the elements. The shape of the cross section is very important because while maintenance on structural elements outside the tunnel can be performed without interruption of traffic, continuous planned maintenance can be performed with a minimum of one tube open for two-way traffic. For this reason, a twin tube configuration or a similar one is recommended. So for example, during standard operation, there must be sufficient space for 2 lanes and a service lane. The service lane can be used for standing vehicles in case of vehicle breakdown, or for the passage of emergency vehicle in case of a traffic jam. Or for example, in case of minor maintenance activities that require access to technical rooms or access to any point along the road for picking up objects, it is better if traffic can continue in 2 lanes at normal speed and service vehicle can park on the 3rd lane. While in case of most maintenance activity, 2 adjacent lanes could be blocked and traffic could continue at reduced speed in the 3rd lane. Blocking 2 adjacent lanes allows safe and efficient maintenance work, while blocking of 1 lane for maintenance is considered too dangerous because this does not provide sufficient protection of workers. Again, if 1 tube is blocked due to major maintenance, for example, after a traffic accident or for cleaning of the entire crossing section, 2-way traffic can be set up in the other tube and a third lane may serve as an emergency lane. So all these considerations, for example, for the Norwegian studies, have brought to the cross section that you see in the picture, doubled, because here you just see one of the two tubes. That allows the scheme for the reduced operation that you can see briefly in the right part. The choice of material. Concrete is a preferred material, respected to structural steel. For the durability shown in the offshore application, in particular for the elements in splash zones and where the use of cathodic protection has no effect. Of course, not all the parts of the structure can be realized in concrete. In the case of tethers, for example, replaceable sacrificial anodes must be provided. If sufficient design life cannot be achieved with great confidence, the replacement of tethers and the connection connectors have to be planned already in the design. So obviously considering also the related cost. For concrete suggestion for proper, I would say, mixed design, these suggestions are known in the application field and new solutions are under development every day. This should be considered in order to guarantee a durable structure and the longest possible operative life for the bridge. For some parts of the structure and for a better inspection, inactive concrete elements should be added to the structure to collect them during the service life and perform destructive testing. So these are pictures from the Furman immersed tunnel concrete testing. You have heard about it several times today, with a design life of 120 years. The choices in the design phase are influencing very much the operation and maintenance procedures from the early design stages. As we have already seen in the previous chapter, the design of ballast system is a key phase, not only for the definition of the structural behavior, but also to define the necessary operations during the life of the structure. So for example, for the Norwegian designs, components which require relatively intense maintenance, such as pumps, are not installed permanently in peripheral location, but stored in an operation center with easy access. In addition, the structure is designed with a passive ballast system, and this means this is meant to remain constant during the life of the structure, with the possibility to modify the relocatable part of the ballast, that is water ballast, only in case of specific situations, like for example, seawater level rising, that are considered in the design. The influence of the design on the operation and maintenance procedure is obviously very important, also for the executive design. As example, inaccessible corners must be avoided in the design of the top anchorages of tethers that are also critical elements for the structure, considering the necessary access with remotely operated underwater vehicles, OV, shown in the picture, for inspection or repair during the life of the structure. And another example could be done, for example, to explain how during the design of the structure, the challenges for the operation and maintenance of the structure must be identified and solutions must be proposed. So the picture is taken from the Norwegian design, where two custom-made tools were suggested during the feasibility study to solve the issues of inspection and cleaning and repair and modification of pontoons. Of course, many design choices are also directly influencing the durability and the maintenance for the structure. This is the case of the design of the fire protection on the inner surface of the concrete shell. To define the fire protection, the local rules must be considered regarding the load to apply. In addition, systems for the thermographic control can reduce the risk for the event. And the picture shows a simulation for fire and explosion in a tunnel. In fact, monitoring is a valuable tool to verify safety and performance of the structure and to gain knowledge on complex phenomena. Precise knowledge on the condition of the structure enables to optimize maintenance work. And these benefits justify the cost for the installation and maintenance of monitoring devices. Monitoring can be used for various purposes. Monitor safety as part of emergency system, so like measuring of the formation, leakage, air quality, temperature, or to verify structural behavior assumed in design for verification of design assumption and a better knowledge on complex phenomena like measurement of strain, deformation, settlements, network frequency, or also wave pressure, wave height, currents, and so on. Or monitor deterioration processes for planning of appropriate maintenance. So measure electrochemical potential of steel, relative humidity in concrete, and so on. If the results of monitoring are critical for triggering alarm systems, redundancy of different sensors and systems can be used for maximum reliability. Finally, and hopefully I'm on time, the availability of the structure is a necessary concept to consider when all the choices are done, from the design stage and when the operations are planned. It is preferable to plan sufficient preventive maintenance, like for example, inspections of ventilation system, traffic control system, drainage system, power supply, and so on, in order to avoid unforeseen restrictions as much as possible. In our experience, I have to say that the acceptance of the road users for restrictions is higher in case of early announcement and explanation of the benefits of preventive maintenance. So as always, do not underestimate the, I would say, the power of communication.